Okay, so here's our last type of Punnett square question. Okay, so far we've looked at monohybrid, dihybrid, incomplete dominance, and codominance. And all of those types of alleles, or those genes, have been found on our autosomes. And what autosomes are the first 22 set of chromosomes. These are autosomes. They carry all of the basic traits for physical appearance and genetic disorder and things like that. Now, so let's label that. So those are autosomes. And we've also mentioned that this last pair, this 23rd pair, these are your sex chromosomes. So sometimes we can also do questions with traits, dominant or recessive, which are located on your sex chromosomes. And it does matter now which chromosome these alleles are on, because males and females do not have the same genotype on the sex chromosomes. So if we're looking at a trait that is located on the X chromosomes, because most of the time when we're looking at traits on the sex chromosomes, they're on the X chromosome because it's so much bigger, and the Y chromosome is so much smaller, and it just doesn't carry as many traits as the X chromosome. So if we're looking at an X-linked chromosome, okay, so a sex-linked chromosome that's on the X chromosome, not the Y chromosome, and it happens to be recessive, we're going to find a tendency for this X chromosome, this X-linked trait to be more expressive in males. Okay, so let's take a look at why that's the case. So for males, remember we talked about how they have an X and a Y, okay, in those karyotypes. And females have an X and an X. So let's just put these in. Okay. And let's talk about, let's just assign a random letter to a dominant trait and a recessive trait, okay? And because it's X-linked, it's only on the X chromosome. It's never on the Y chromosome because it's X-linked. So that means on each of these X chromosomes, we have to assign either the dominant or the recessive allele. So for male genotypes, there's only two possibilities for that male's X to carry a dominant, and we write it as a superscript up here, a little tiny letter that's kind of up to the right. Or that male can have a recessive allele on his X chromosome. Now there's nothing, we don't put anything here because it's not a Y-linked chromosome. It's an X-linked chromosome. Okay, so we can see that males can either be 50% chance of having the dominant allele or a 50% chance of having the recessive allele. But for females, because we have two X chromosomes, there is going to be three possible combinations of dominant and recessive, just like we've seen. We can have two dominants, okay? And because we have two, we have to assign an R to each of these X chromosomes as X-linked. Or we can have one of each. Or we can be homozygous recessive. So you can see here that we have three possible genotypes where males only have two possible genotypes. So if this was a trait or a gene that controlled a genetic disease, for example, and this disease came if you had the recessive allele, that means that this individual, this male, would have the disease. That males would have a 50% chance of getting this disease. Okay, but for females, the only way we could get this recessive X-linked disease is if we had this genotype, the homozygous recessive genotype. And that's a 33.3333 so on % chance. So you can see that what we've set up here, a recessive trait located on the X chromosome, is definitely more likely to express itself in males. This is why males have a higher rate of colorblindness, because colorblindness is a trait that is located on that X chromosome. So as males have a 50% chance of being colorblind, and females have a 33.3% chance of being colorblind. Okay, so let's go on and do a question actually involving color blindness. Okay, so in humans, the recessive allele that causes a form of red-green color blindness is found on the X chromosome. So right away, that tells us it's a sex-linked trait, and specifically, it's an X-linked trait, okay? Not the Y. And it also tells us that color blindness comes from a recessive allele. So I'm going to go ahead and put that this B, representing blindness, color blindness, is going to be the recessive version. And the capital dominant B is normal vision. Okay, and we can go in and put color blindness in humans. Okay, now the setup here for the parents is a little bit different. Okay, so let's go in and it really and put it in. It really makes a difference that you have to put in the gender here for the phenotypes and the genotypes. Okay, so we have a colorblind father. Okay, so let's go in and do that. We have a colorblind father. It's important that we put father, crossed with a mother who is homozygous for perfect vision. But for phenotypes, all we care about is that she has perfect vision. Okay, so I don't care whether you put perfect vision or normal vision. It doesn't really matter. Okay, so we have normal vision here. A normal mother. I'm just doing this to save some space here. So a father who's colorblind and a mother who has normal vision. Okay, so the next thing is really important, the next step. To put in the genotypes, you can't just do it like a monohybrid cross with the dominant and recessive allele. You have to actually go in and do the father's genotype with the XY and the mother's genotype with the XX. And I'm going to use a different color to show our superscripts. So the colorblind father, because he's colorblind, he has to have the dominant or the recessive B on his X. Okay. And the normal mother, because she's normal, she could either be homozygous dominant normal, or she could be heterozygous normal. Either way, the law of dominance still applies. This is why the question has to tell us that she's homozygous for perfect vision, which means that second allele has to be dominant as well. Okay, so therefore, when we figure out the gametes, we take a look at the father. The father can give his child either his X chromosome or his Y chromosome, and the mother can give her offspring either an X or an X only, with the appropriate assigned B's on them. Okay. So then let's go in and put in our gametes up here on the Punnett square, the father on the top, and the mother along the side there, and put the B's in correctly. Now, again, it's important for the offspring, put in the X's and the Y's first, and then assign the B's after. Okay, so we know, hopefully, at this point, that to have an offspring who's male or female, we have a 50-50 chance of having either gender. So this is going to show up in our Punnett square outcome. So we can see here in this column, we're going to have our 50% females from this gamete and these gametes. Okay, so then we're going to go in and put in the B's. So we have one dominant B and one recessive B for this offspring. And we have one dominant and one recessive allele for this offspring. So both girls, both offspring that are girls are going to have a heterozygous genotype. Okay, so let's go in for the males. So again, we always put the X first for an X and a Y for the males. Okay, and now we're really just looking at the B's that are on the mother's chromosomes, okay? Or on the mother's X chromosome. So we have here a capital B from this one and another capital B from this one. Okay, so we can see here now that we have if this couple has a daughter, she will always be heterozygous, so she'll have normal vision. And if this couple has a son, he will also always have normal vision. So what is the question? Identify the phenotypes and genotypes of the F1 generation. Okay. Oh, shoots. Let's go back up here. Where did we go here? Okay. So therefore, I'm just going to change my color here. Therefore, the genotypes are, and you can just short form it like that, and we're going to have to list just the two different kinds. Okay. Okay, because we have a 2-to-2 ratio going on here, and what do we have to do? Reduce. Okay, and the phenotypes. And again, you have to put gender for this one because it could end up where both of the daughter scenarios are different. Okay, so you have to put gender for the phenotypes. So you can put normal daughters to normal sons equals 1-to-1. Again, I already reduced in my head there. Okay, so that's how you would do a sex-linked question. Okay, so the next one here is your final option here. I think, oh, there's one more. But if we go through and look at this one, it's the same setup. Okay, we're still gonna, I'm not gonna rewrite this whole thing again because it's the same color blindness in humans. Let's just go in and jump right into parent phenotypes because we have a different couple here. We have a father who has perfect vision and a mother who is colorblind. Okay, so a normal father and a colorblind mother. Okay, so let's go in and put the father's and the mother's X and Y chromosomes. And the father is normal, so he has to have the dominant B on his X. And the mother is colorblind. Okay. Oopsies. Look at this question. That doesn't make sense. So I did a mistake here because we have heterozygous for the colorblindness trait. She isn't actually colorblind. So let's go and erase that. She is heterozygous for colorblindness, which means she is also normal. So let's change that. My fault there. Whoopsies. Okay, so she's heterozygous for colorblindness. She is normal, so that means that she has to have at least one dominant if she's normal, but she's a carrier. So that's a term we also use for the heterozygous genotype, especially when we're discussing genetic disorders and diseases, where someone can be a carrier of the disease, but they're actually healthy. So that just means that they could pass it on to their offspring, even though they themselves are healthy. So that's another term that we can use for a heterozygote. Okay, so we go on and we do our gametes. And you can use a comma, or you can write the word or. It doesn't really matter. Okay, so we're going to go in and fill in our Punnett square here. So the father is healthy, the dominant B, and the mother is heterozygous, which means she has one of each. Okay, so we'll put in our offspring X's and Y's. and then we'll assign the B's. Okay, so the first daughter option here has 2 dominant B's. The second daughter is heterozygous. The first son has a dominant B, and the second son has a recessive B. So the question is asking for the phenotypes and the genotypes of the F1 generation. Okay, so what you would say is you would literally list all of the genotypes, right? All 4 of them, and you would put them in a 1:1:1:1 ratio. And then you would just list the phenotypes, and you would say 2, you would have healthy normal vision daughters, and there would be 2 of them, okay, to a healthy normal visioned son to a colorblind son. So you would have this ratio of 2:1:1. Okay, so that's how you do the X-linked or the